Welcome to MFC Group's FasTech seminar series hosted by FH Sales. Thank you guys for joining us this morning. Today we're spotlighting easy EMI and RFI filtered connector solutions from the design process through production with Quell. Our speaker for this seminar is Scott Lindberg, president of Quell Corporation, who has over 20 years of experience in the industry. Everyone is muted, so please type any questions you may have into the meeting chat, and I will be sure to monitor those throughout the presentation. And we will open it up for Q&A at the end. And Scott, I will turn it over to you.
All right. Well, thank you very much, Amanda. Hey, welcome everybody. We're going to go fast and furious here, get you back onto other things real quick, but we're going to talk about EMI, RFI, transient suppression, and different ways to mitigate some problems. First, I want to thank FH Sales for putting this all together. FH Sales has been our rep in that region for several years. They represent a lot of different lines, and I threw those up here. One of the best things about a manufacturer's reps is they solve problems for you, the customer. They bring a lot of different things to the party, so when they come to you, they've got different solutions for different things, and they understand you and what you're doing certainly better than we do sitting down in Albuquerque, New Mexico. A little bit about me. I started as a manufacturer's rep back in 1983. I left the rep business in 2004, went to the manufacturing side, started doing semiconductors with a company called Advanced Power Technology, moved on to micro semi, and found Quell 10 years ago down in Albuquerque and have been with them ever since. I started as their director of sales and now am a president of the company. I also do some other things, a lot of industry involvement. And you know what, we all do this for our making some money for our family. So I always like to share my family with you. I've got 4 children, my son Michael on the left, my daughter Lauren, there's my wife Cheryl, and then I've got Sarah and my daughter Carly, my son-in-law Ethan on the far right, and my 2 grandchildren, which is just really, it tickles me every day. So, all right, enough about that. Hey, Quell Corporation is in Albuquerque, New Mexico. We have about 45 people today. 12,000 square feet down there. Everything we do is manufactured in the United States. We'll talk a little bit more about Quell. Our history, we're not a new company. We were founded in 1994. We've done lots of different things. Today, we've sold or supplied over 2.5 million pieces of our product into military, defense, aerospace, and just high reliability applications. We were acquired in 2019 by a company called HEICO. HEICO is about a $2.5 billion company. They own about 80 different subsidiaries in the aerospace and military arena for the most part. Our products are called EE-Seal, and I'll get into this in a little more depth later, but you can see some of these products. We go over the pins of a connector and make a filtered connector pretty quickly. We also can go over the rear of the connector and make a filtered connector very quickly as well. But today I want to talk about a few different things, a little bit about the design process, what you go through as a customer in your design, the testing, some of the options you have, then specsmanship, because it's really interesting when we look at filters, what we see in the specsmanship of some of the parts that we get sent to us. PDQST, which is price, delivery, quality, service, technology, and then performance. I've added a P here as well, and then some of our solutions, we'll get into that. All right, what do we do or what do you do? When you're looking at EMI, typically you're trying to solve problems. And we're typically trying to solve problems for any source of a problem or any victim of the problem. And we're trying to do usually mil standard 461 or DL 160 issues, but it could be other specifications as well. We're trying to do radiated emissions, radiated susceptibility, conducted emissions, conducted susceptibility. That's where we're really focused, right? And in the design process, when we start the design process, obviously you do the planning and development, and then you get into the design. And when you get into design, that's really the critical area where if we can mitigate all of our issues in the design, we won't have EMI problems, because that's the goal, is not to have them. So in the design, we design our boxes with capacitors, TVSs, MOVs on the board, or we might do inline filters or power line filters. We'll do shielding, right? The goal is to solve the problem before we get to test. Then we go to test and we do our EMC testing. If everything works well, we're off to production and life is good, right? We don't have to worry about anything else. We're just off to production. On the other hand, we go to EMC testing and we find out we've got an issue. We failed our EMC test. We have a couple of options. We can either go back to design and redesign, or we can go to production, right? But to go to production, we got to solve it in the lab. So if we go back and redesign, there's a lot of costs involved in that. So we have to spin that board, which is costly. We have to scrap material. We have to go back and reschedule a test. And the time that that's going to take could be 6 months. It could be a year. And the cost of going back to testing, I've heard some numbers when people are doing their testing that it could cost $1 million or $5 million if you're testing a piece of, let's say, a Humvee in the lab, all the costs that are associated with that. So it is very costly to go back and do a board spin and do all that testing. So if we can solve it in the test lab, then on the other hand, by throwing ferrite beads on it, doing some shielding, doing whatever else that you can do in the test lab and get you to production, that's going to be better. So from a connector standpoint, there's lots of different things that we can do in connectors. So filter connectors typically use a planar type filter or a discoidal filter, or they'll use tubular capacitors. We typically use discrete devices in our device. Looking at filters, there's lots of different filters, but the goal is to get us out of the lab and solve our problem. So we can use a C filter, an LC filter, a pi filter, or whatever kind of filter we want. But the key is we want to get out of the lab and get into production. When you look at these different filters, they have different levels of attenuation. So the best filter that's out there theoretically is a pi filter, and it's going to give you the lowest insertion loss and the highest attenuation. A C filter, on the other hand, is going to give you the least amount, right? But the key, again, is to get us out of the lab. So what's the best option between all these? Well, it's the one that solves the problem, right? So we've got outages here, and if we can solve that problem, it doesn't matter which one we solve it with. If we can solve it with a C filter, as opposed to a pi filter, that's probably the best option. If we need a pi filter, you need a pi filter, right? So one of the things I want to show and share is the specsmanship that we see here at Quell, because we get opportunities or questions, can you cross this device and compare it to something different? So somebody comes to us and says, hey, I have a spec. I need you to meet this spec. So this particular device, this is a feed-through plate. It has feed-through capacitors. I think there's 10 here. These are 5,000 picofarad device plus 100% minus 0, 100 volt devices. And you can see the attenuation that the spec has. It goes up to 70 dB. This is a great filter, 70 dB at a gigahertz. So they asked us if we can second source it. This customer had a lead time problem, they had a cost problem, and they had a quality problem. They were actually cracking the inductor. This is an LC, so they were cracking the inductor here, and so they had a quality issue. So they want us to meet 70 dB at a gigahertz. So we actually got a sample of the part so we could test it. This red dotted line here is the spec, right? And you can see they get 70 dB at a gigahertz. That's what the spec says. But if we measure the part, that part doesn't meet the spec. And we find this a lot where the specsmanship that people give us, they say, can you meet that? And our answer is no, we cannot meet that. We don't come close to that. But then we look at the part that they're getting, and that doesn't get close to it either. But what we do is when we go into the test lab and we test our part and it passes, and it solves the problem. That's the key, right? So we took this exact part and we did the same thing using our discrete, just a C filter, right? So we didn't have the additional farad inductor here. And we compared it. And so we put this into a D sub to test it. And you can see where our part has lower insertion loss, greater attenuation at the lower frequencies, and then it matches it at the higher frequencies for the most part. Not when we get to a gigahertz. We fall a little bit low on that, but we do match for most of the frequency mitigation. Now, can we second source that? Right? The second source of a filter is very difficult because this particular part has been tested in the system and it worked. Ours will perform better. When I say that, it gives you more attenuation, but is that actually better? And the answer is you have to test it. Because if you've got data rates here that are pretty higher frequencies, and I give you 20 dB of attenuation, I may remove your data, right? it's a better filter, but it may not be the right filter for this application, right? But it kind of meets the spec of the other guy. And so this happens quite a bit. So here's another, looking at two different filters, same capacitance in both of these. The blue lines are a pi filter from competitor A, right? And the green line is our pi filter from competitor Q, we'll call us, right? Ours performs better. Again, what is better? Better has more attenuation, but it doesn't necessarily mean it's going to work in the circuit, because it may have too much attenuation versus the other part. Solving the problem is really, really the key. That's what we want to do. So here's an example from Quell, where we had a customer who gave us their baseline specs without a filter from 2 megahertz up to a gigahertz. And you can see all the various outages. We always try to be cost effective. And so we ask lots of questions. So our first design, trying to be cost effective, was to put three devices on each pin. 347 nanofarad caps, 500 volts, to try to solve the problem. The customer put that in, and this is their results. And it didn't solve the problem. It didn't solve the problem. They're in the lab. We sent them apart in 24 hours. They got it. It didn't solve the problem. So we went back to the drawing board because we needed to mitigate a lot of noise. So we ended up with a design that had 12 different capacitors. So this is the attenuation curve. And when you put multiple capacitors in there, if you put the same value in, it actually increases the attenuation slightly. If you put different values in there, they actually act separately. So you could measure the total capacitance in here, which I didn't actually do, but it'd be about, I don't know, 2-point-some microfarad. But these are going to mitigate noise, kind of like these curves. So if you look at the difference in the two designs, the first design, we added only 3 capacitors per pin. The second, we added 12 devices. This is a far more expensive part, but we got it to the customer while they were in the lab, and we solved the problem. So if you now look at their baseline spec versus version 2, we've solved the problem. We got them out of the lab. In this application, they only needed 50 parts. So it really didn't matter what the cost of the part was. They were spending $250,000 a day in a lab for this military vehicle. So the key was to get them out of the lab and get them into production. Here's another example of what we see in the lab. This is a customer that went to the test lab, and you can see the ambient here is this gray line. And then you see their outage. So I love this one because the customer actually didn't believe that our product would work for them. And he did his original test in black, and he's out all over the place. He dropped a EE seal in there, and he got this red line. And he said, that doesn't make sense, because that's basically the ambient temperature inside the chamber, not temperature, ambient noise in the chamber. So he extracted it, and he said, all right, let me confirm I'm out. And he confirmed with his green line, and he put it back in, and he confirmed with the blue line, and he came back because we solved the problem. And he says, wow, this thing worked, right? And he had to do it twice to test it. All right, so now let's talk about PDQST, price, delivery, quality, service, technology, and then performance. When you look at any product that you're buying, this doesn't really matter for EMI filters, but I coordinated this for filters. Anytime you're looking at a product, you're really looking at PDQST-P for performance. So price, if price is an object, it always is an object. I've had people say, hey, price is no object, just solve my problem. And I come back and say, well, that's a $100 solution. They go, oh, that's too expensive. So price is always an object. So when you're looking at filters for connectors, a C filter is going to be the least expensive. A pi filter or T filter is going to be the most expensive. Delivery, C filters are going to be easier to get than pi filters. Quality, they all have to have good quality. If you don't have good quality, you've got a problem. Service and technology, typically that is company dependent. So you're going to have to rate that based on that. I think our service is outstanding. I think our technology is really, really cool. And performance is really the key. It has to solve your problem. Again, I look at this for EMC or transient protection side of a connector. But you can do this for whatever you're looking at. If you're looking at MOSFETs or diodes or shielding materials, you can look at it for anything. All right, the Quell solution. What we do is we make a product called EE-Seal, which is a silicone rubber packaging technology where inside the silicone rubber we embed chip devices, typically 0402, 0603 devices, sometimes smaller, sometimes larger. And we put them in there and we make a circuit, a custom circuit that matches your application. And we put it over the pins of the connector, just gently put it over the pins and use the mating connector to seat it at the bottom of the connector at the interfacial seal. There's no soldering, no tools, just the mating connector. We do this for EMI, RFI. We do it for some transient protection, some levels of lightning. We can do grounding. We can add a pull-up resistor and things like that. Anything you can think of that we can stick inside, we can do that. So if you look at the EE-Seal and the design, so we're going to go over the pins of the connector. Now, around each pin, we have several different designs. I'm only going to touch on a couple of them today, but we have conductive silicone that gives you 360-degree contact around the pin. Then we use 3 neal copper gold-plated wires to make a connection to a capacitor, and then that capacitor will take either pin to pin if you need, or pin to ground to make a C filter. Right? We can also do multiple devices. We can do series and parallel configurations if there's room inside the connector. We also have conductive silicone that makes our contact with the plug or the receptacle, depending on the need. Right? So it's a very flexible product. We go inside the connector and we add about 30 mils after mate in here, but we maintain the pin to socket connection here. Right? And because it's a three-dimensional product, because it's silicone rubber, it conforms to all the nooks and crannies inside the connector. So we mimic the cork and bottle aspect inside of here, which is a 38999 cutaway. Because we use discrete devices, as opposed to a tubular capacitor or a planar, first of all, our lead time is much less because it's all discrete, but I can also treat every pin uniquely. So we always ask, what are the signals you have on your pins? What are the voltages? What are the data rates? If you've got here, for example, 12 megahertz data rates, and I put a 47 nanofarad capacitor on it, I will get rid of your noise, but I'll get rid of your data. If you've got video signals or Ethernet, we'll treat those or not treat those respectively. So every pin can be treated uniquely. If you have 120 volts, 400 hertz, and I put a 50 volt cap on there, you won't have that capacitor for long, right? So every pin can be treated uniquely. What happens in our world is we showed some of the scans, but here's an example where customers failing at about 50 megahertz up to 200 megahertz with a 15 dB spike. All we do at Quell is we come here and say, all right, from 50 to 200, the peak spike's about 150. We're going to probably use that 1 nanofarad or 1,000 picofarad device, and we're going to put it in there. We're going to try to solve that problem. We put it in, and if everything goes according to plan, you, the customer, are going to get that green line and you're off into production right away. Parallel capacitors. I mentioned we can put multiple devices inside. So there are times when we can't get all the frequencies, kind of like that example of that military vehicle where we ended up putting 12 devices on it. We need to put multiple devices inside. And this can be done as long as there's room inside the connector. This particular connector here you should see is a 3215.3. This is a device that goes into the M1 Abrams tank. Here we have 6 1206 capacitors protecting this one power pin and 6 1206 capacitors protecting this power pin. They're in series and parallel to get higher voltage, higher capacitance. So we effectively get 0.71 microfarad of capacitance on each of those two pins. These 4 with squares have a 47 nanofarad capacitor protecting these signals, and these are open. So it's really what makes sense for your design, for your application. That's all about EMI, but we also have the ability to do some transient protection, either ESD or some levels of lightning. We can't do direct lightning strikes, but we can do some levels of lightning. One of the applications we have is for a composite aircraft called the 787, where they were grounding this aircraft daily due to lightning strikes. The average aircraft gets hit, this is my research, 1 or 2 times a year while it's flying. Well, in this case, they were sustaining a damage to a bunch of boxes, and it was grounding the aircraft, which, as you can imagine, Boeing doesn't like. They needed to protect against 250 amps worth of current on one ground return pin. We did 4 different iterations before we found the right solution for them. And we ended up with this device here, which has 15 MOVs. They're all matched in parallel, protecting that one pin. Now, if we had to protect all the pins against 250 amps, we couldn't do it. But because we're protecting just one pin, we could. The customer tested the box. They environmentally qualified it to the customer's spec. They retrofitted the entire fleet of 787s at that time. We've been selling this product since 2015. Today, there are 75 to 100 of these on every 787. And I'm a little behind. We're at about 110,000 parts that we've shipped so far on this. I need to update that slide. Another product that we have is called EE Seal Plus. EE Seal Plus is our next generation product. So the conductive silicone that we use for our contacts, we now here for EE Seal Plus get 360-degree contact around each of the connectors, or to make contact with the shell or the plug, and we get 360-degree contact around each of the pins as well. This gives us a little additional attenuation, but it also allows us to do something very unique. We use discrete devices, still 0402, 0603, but we can also make an integral capacitor. A capacitor is basically a series of dielectric and conductors. Well, we're using conductive material, so we just use a dielectric in the construction of it, and we can get a very low capacitance device that will give us high frequency mitigation. So if you look at this, this is the cutaway of this. So we have this highly conductive ground plane, this brown, and then we have non-conductive material. So we have a conductive piece of material around each of the treated pins, right? And then we put a non-conductive ring around that. So we make connection from pin to the conductive material through the device to the ground plane, right? That's using a discrete device. If we want to make an integral capacitor, you basically remove this capacitor and you change the dielectric of this non-conductive, and now we can get very low capacitance to get high frequency mitigation. If you compare the two, again, specsmanship, right? We try not to do any specsmanship. I want you to know exactly what we can do, right? And the proof is in the testing. Here you're looking at a EE Seal in blue and an EE Seal Plus in red. The EE Seal uses a 2200 picofarad or 2.2 nanofarad device, and here we're targeting 80 megahertz. The red dotted line is the EE Seal Plus. To target 80 megahertz, we would use a 6800 picofarad device or 6.8 nanofarad capacitor. Notice that we get a little more attenuation because it's a bigger capacitor, both at the peak and up and down the curve. So it performs better, but again, when I say better, it has to solve your problem. And if the EE Seal solves your problem, you may want to use the EE Seal over the EE Seal Plus, right? If you look at the same device, now we're going to use the same capacitance in 3 different devices. So we're using a 4 picofarad device in an EE Seal Plus, and an EE Seal Plus with the integral capacitor. They all work different. So if you ever go to a filtered connector manufacturer and say, hey, I need you to put a 4 picofarad device in this, that may not be the right solution because the inductances in the device or in the circuit are different for everyone. So here you can see if we put it in an EE Seal, we're pretty much targeting about 2 gigahertz. If we put an EE Seal Plus, we're going to be about 3 gigahertz. If we use the integral capacitor, we're mitigating noise from 10 to 100 gigahertz. So it changes depending on the inductance inside the devices. The other thing that we do is we do make filtered connectors. This is at the request of our customers because somebody came and said, we need to go over a socket because we don't have control over the pin side. Well, since we can't put an EE Seal over a socket, we ended up doing some things with standard components for a connector so we can embed it on the rear of the connector. In this case, we actually have 2 EE Seals because they needed to pass higher voltage for high pot testing. So we put 2 EE Seals in a barrier and potted it and gave them a completed solution. Same thing here. We're using an adapter ring to give them a connector solution that works for them, or an audio connector here. This one is not potted. It's shown before it's potted. We can also now do pi filters on the rear of the connector as well. Everything we do has to be rugged and reliable. Quality is the most important thing in your PDQST P analysis. You have to have quality. Our parts have all been environmentally tested. Our original environmental test was funded by Boeing for the CH-47 helicopter. We just redid our test and increased it to match the MIL 461 and DL 160 specs. So it's gone through all these different things, shocks, vibration, and things like that. We've done through the durability test because it has to meet 500 mates and demates. It sits at the bottom of the interface, and so we've tested it for 500 mates and demates to make sure it works for that. We also do outgassing. We can outgas to meet the NASA specs. We've been flying in space now for 19 years in all sorts of different black satellites and launches. I would say pretty much almost every space launch has our part in it. We have another new part that we've introduced that we honestly haven't sold any yet, but we're very, very close to selling some for some space applications. This is called ESD seal, and it's a highly resistive device. It's designed for ESD issues in space or cable assembly. If you're doing a cable discharge and you bring a cable across to assemble it, it will mitigate the ESD there. It's 10 to the 7th, 10 to the 10th ohms. Brand new. It's only been out for about a year, and I've got about 40 different source control drawings that we're close to being on. So excited about this. I do have some videos that we can share with you later. I mentioned we can do some simple things like gaskets. We really put electronics in gaskets. And I went to a customer and they said, "Can you just do a gasket with nothing in it?" And I go, "We don't do that." And he said, "You put holes in silicone rubber, don't you?" And I said, "Yes, I do." So we became in the gasket business. So we can do non-conductive. We can do cut conductive gaskets where we're just grounding a shield, or we can even do a short. Right. And we can do some external gaskets as well. And our claim to fame is really quick turnaround and reliability. So if you look at this, we don't really care what connector you go into. It can be a custom connector. Typically, we're going into a lot of circulars, 38999s, 2642s and such. Well, the smallest connector we can do is a micro D. We can't do nano Ds. It's too small. There's not enough room for the capacitors. Do a lot of D subs. We can even do plastic connectors. Plastic connectors have a different problem because there's not good grounding. So we'll need a grounding path, but we can do pin to pin very well inside of a plastic connector. And we really don't care whose connector it is. It's your connector. We like to use a standard connector because we can get those off the shelf very quickly. Everything is custom. It has to match your application, so every pin's exactly per your application. We can go pin to pin, pin to shell, as I've said. There's no tooling cost for what we do. We do have an NRE charge. That NRE charge is minimal. It's anywhere from $350 to probably $1,200, depending. If we get into a filtered connector, it might be a little bit more. Two things we don't talk about enough is we don't take any additional space because we go inside the connector, right? And it's very lightweight. So if you're doing a man pack for military, you're doing something in aerospace, it doesn't add a lot of weight. It's also something that you can use for retrofitting a device. We have one that we did for the A-10 aircraft. It would take off in Afghanistan. It went past us radar station and the chaff dispensers kicked off. Well, the pilot didn't want that. He was not happy. We designed a part. We shipped it to them. They put it in. It solved it. They retrofitted the fleet. Everything we do is custom. So everything we do is custom. We don't really have any standard products, but it's a standard process for us. We think we're relatively fast. If you tell me right now that I've got a part, I've got a 6-pin part that I need, and this is what I need on each of those pins, we're early enough in the day, we can design, build, and ship that part tonight. Typically, if we get something that's a simple part, by 2 o'clock in the afternoon, we can ship it the same day. We'll guarantee we'll ship it in 48 hours. Right? And we ship that for free. We ship it for free because typically you're in the test lab and you need it right away. And if we have to get a purchase order for it, the purchase order may take a week to get us the purchase order. We'll ship it for free. We also ship it for free because we want to solve your problem. And I don't want you to spend, $500 to get a sample out and put it in and have it not work. I want it to work. We want to show you it works. And if it works, then we're off to production. Lead time right now is actually 8 to 10 weeks. We're trying to get it back down to 6 to 8. But the key here for lead time is that we want it to be better than that. If you need it to be 5 days, we will find a way to get you an amount of parts in 5 days. We'll charge an expedite fee for it, but you need it when you need it, and we're going to do the best we can to get it to you at that time. From a cost standpoint, our biggest competitor is a filtered connector, and we believe we'll save 20 to 50%, maybe even more versus a filtered connector solution. And we'll save you a lot of money in terms of not having to go back and rework, not having to scrap, not having to reschedule test lab time and things like that. Typical customers, lots of different customers. This is kind of who's who. If your name's not up there, send me a logo and I'll put you up there. But we're probably selling to your companies already. It is a high value electronic device. This is not going into a blood pressure cuff for home use. This is not going into a Dell laptop. This is going into a tank or a missile or an aircraft or a helicopter. What we need from you to be successful for EMI is these 6 questions. This is all we need. We need to know your connector part number, where your frequency outages are, or what capacitor you'd like. I like to see the scans because then I can target exactly where the big outages are. But we have people say, hey, can you put 47 nanofarads on all the pins? And we'll do that as well. Need to know the voltages and the data rates, as I'd mentioned. If there's any transient specs you need to meet, we'd like to know that, and where do we ship it? And we'll get that out to you in 24 to 48 hours. The website has all of this information. I'm going to pass on a PDF version of this that Amanda can send to everybody if you'd like. Just let her know. But the website's got all of this. The website has a video on it. And I don't know if I shared my screen for the video. Let me unshare and reshare really quick just to make sure, because I've got a video that was done by Jay Skolnick. Jay Skolnick is a consultant. He does EMI, RFI consulting. And hopefully I didn't mess that up. And he came to our office and said, hey, I'm interested in having a tour of your facility. And we said, all right. We showed him a tour, and he went away and he designed a box to demonstrate our product and how it works. So hopefully the sound will come through on this. Man, if it doesn't, let me know right away. But here's a little quick 1.5, 2-minute demonstration.
Welcome to the Skolnick Technical Training Institute. Our trainer, Mr. Jay Skolnick.
In today's demo, we have an electronic control unit, or ECU. This unit could be in an aircraft, tank, or automobile, and could be for controlling the engine, a missile, or the airbags in the car. Imagine this ECU is in your application. Inside our ECU is a power supply, analog and digital electronics, along with a microprocessor which is running the code. Power is applied in the front of the unit, and the solid green light shows the unit is functioning properly. The red indicator light will alert us to any event that interrupts the microprocessor. This could mean a false airbag deployment, an inaccurate missile warning indicator, a misguided missile, engine stall, or other unwanted event. In today's demonstration, we will first show a radiated susceptibility issue caused by an ESD event. Next, you will see a conducted emission issue being generated from the electronics inside the ECU. Finally, we will show solutions to both problems. A radiated susceptibility problem is caused by an ESD event where our ECU is subjected to a voltage spike of 1 kV. This transient causes an interruption of the microprocessor, the red indicator light flashes, and an audible tone sounds to signal the event. Moving to the issue of conducted emissions that affect our unit, we will use a spectrum analyzer. The spectrum analyzer shows EMI issues with our ECU at 50 megahertz, as well as some other smaller spikes in the 10 to 30 megahertz range. To meet the required specifications, we must mitigate both the EMI issues as well as protect our unit against transient or ESD events. In our effort to solve our problems, we are going to use an EE seal from Quell. The prototypes are delivered in 24 hours, and inserting the EE seal into our MIL 5015 connector is easy. We simply place the EE seal over the pins of the connector until the pins protrude through the holes. Once in place, we're using the mating connector as our insertion tool to secure the EE seal and create our very own filtered connector, including ESD protection, in seconds. Now that we have our EE seal in place, we can retest our ECU to see if we have solved our issues. First, we apply a 1 kV event to our ground plane, and the green light remains lit. and we receive no indicator or audible tone that a transient has affected our box. Next, we look back at our spectrum analyzer to see what changes have occurred in the EMI noise affecting our box. As you can see, all frequencies from 10 to 50 megahertz have been mitigated and are no longer an issue.
Today's ESD and EMI solutions were fast and effective. If you'd like additional information on today's product solutions from Quell, visit www.eeseal.com. The Skolnick Technical Training Institute is proud to help companies all around the world learn more about ESD and EMI. More information on the Skolnick Technical Training Institute can be found at www.skolnick-tech.com.
All right, I love that video because it's he did it on his own for his own training, and it's probably the best marketing tool that we probably have to show how easy it is to use an EE seal. So that's online. If you want to share that with somebody else, you certainly can. All right, I love this. It's a little cartoon I found. Uncle Jay, what do you know? Do you know why hummingbirds hum? This is a great EMC joke. Bad filter capacitors. I don't know if that's funny or not. I liked it. Hey, I appreciate your time. Are there any questions? Open it up.
I'm actually going to unmute everybody so that if anybody has any questions, you can just ask them in case if you have trouble with the chat. And I'm also going to launch a quick poll if you guys could give us your feedback.
Any questions, or did I answer everything right off the bat?
Let me check our chat here. If we have any, we currently don't have any questions in the chat, but if anyone has anything that they'd like to ask, please feel free to put it in the chat, or you can unmute yourself.
All right. Well, being that I don't hear any questions, let me do this. One, first of all, thank you very much for your time and attention. Time is valuable, and you've spent looks like about 37 minutes. I appreciate you giving us the time today. If you have any questions, the easiest place to ask them, just send an email to, they send it to me, just send it to Scott, SCOTT, at quell.us, and I will answer them. Or you can also send it to eeseal at quell.us, and I'll have about 3 or 4 people that can answer it. EESEAL at quell.us. So, all right, Amanda, I think that's good. Thank you so very much for setting it up. Thanks to FH Sales.